Hello, 1324 students. We're going to be talking about section 9.2, which really kind of belongs back in chapter 8. It's mostly about how to count things, a particular set of things. It's going to be discussing factorials, permutations, and combinations, and how even if after you know about those things, you don't always have to use those formulas. Okay? So, for example, factorial, when would you want to use that? Well, suppose you have a question like this. You have 9 players on a baseball team. How many different hitting orders are possible? How many different lists of those 9 names could you submit as the hitting order for that team? Well, if you just draw 9 blanks and ask yourself, right, how many choices do I have for the first one? Well, there's 9. And then after I put that person down, there's only 8 left. For this one, 7, for this one, 6, and so on. And then you use the counting principle. You're multiplying these number of choices. You multiply all those numbers together. Well, that's what we call 9 factorial. 9 factorial is 9 times 8 times 7, and so on. Just like 5 factorial is 5 times 4 times 3 times 2 times 1. You could group things and get 20 times 6, it's 120. Or you could do over here, and numbers larger than this, when I'm taking their factorial, I just use the calculator, which has a probability section that you want to get familiar with. So you go to the math section, and there's 4 categories across the top. The last one is probability on the far right, which you can get to quickly by just wrapping around left. So now we're in the probability menu. We have things like NPR for number of permutations, combinations, and factorial. So here's that factorial button. Well, if I pick it now, it doesn't have anything to take factorial of. So to use it, you have to put in a number first. So 9, math, probability, 4 for the factorial. There's my 9 factorial. There's my 362,880. Different batting orders. Why would you want this sort of thing? Well, soon we'll be asking, what's the probability that a given batting order was chosen? So if somebody listed all 9 names, particular names in a particular order, the probability of choosing that one list would just be 1 out of 362,880. Okay? Second example, suppose you have 85 recipients of special honors to read off at graduation. And how many different ways could you read off those 85 names? Let's say alphabetical. People did not want to use alphabetical. That's one of those orders, but let's we want to change it up. Well, how many different ways could you change that up? Well, it would be 85 factorial. But if you try to go to the calculator with that, it says error overflow. Because it turns out that 69 factorial is the biggest factorial our calculators, your graphing calculators, can withstand. That's 1.7 times 10 to the 98. Notice that if you try to do 70 factorial, that would be equal to 70 times 69 times 68. Well, that's just dot, 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 and that's the same thing as 70 times 69 factorial. So that would be the same thing as 70 times that number there. There's a 10 in there, that boots it up to 10 to the 99. There's a 7 over there times 1.7. That's greater than 10. So this would be over 10 to the 100. That's just 70 factorial. What are we going to do about the 85 factorial? Well, 85 factorial is a pretty nice simplified way of stating that really large number. But does everybody understand how big a number that is? You could go back and say, well, that's 85 times 84 times 83 dot, 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 times 71 times 70 times 10 to the 98 to give people an idea. Some idea. All right. Now, so with factorial, you can't go to the factorial button with a number bigger than 69. But there's lots of problems in your book that ask you to use permutations and combinations, numbers much larger than that. Looking at the formulas for permutations and combinations, I think you guys can see that. Where is the glare? How about there? That's better. Okay, So look at this formula. For permutations, it's n factorial over n minus r factorial. So you're going to be taking one factorial divided by another. Well, when you do something like that, for example, 99 factorial over 96 factorial, that looks like 99 times 98 times 97 times 96 and all the numbers below that. In other words, 96 factorial over 96 factorial. Those all cancel. Those all cancel. There we go. 96 factorial cancels with the 96 factorial. You're just left with 98 times 98, 98 times 97, which is 941,000. Not such a big number, really. So permutations and combinations, you're going to be going to them with n and r very large numbers, no problem, because they are ratios of factorials which cancel in this nice way. All right. For example, why would you want to go to the permutations button? Let's suppose I have 10 favorite books, and I'd like to put 4 of them on this lovely special shelf I have in the living room. But I'm trying to figure out. I'm sitting there going, how many different ways could I choose 4 books out of those 10, and in how many different ways could I arrange those 4, right? So that could lead to your, and while you're at it, like how long would that take you to do, right? Let's say it takes you 5 minutes to choose 4 out of the 10 books and put them up on the shelf and look at that particular arrangement. 5 minutes for each arrangement, let's say. How long would it take to examine each of these arrangements? You gotta know how many arrangements there are. You could use NPR. That's the number of permutations of n things taken r at a time as follows. So there's n equal to 10 things to choose from. You'd like to take 4 out of those and you put them in particular arrangements, permutations. So you use NPR, what you enter is 10 NPR 4 in your probability section. Right, so you go to math, you wrap around to probability, you go down to NPR, that's how you grab that function. And again, of course, we need to put the number in first. So it's 10 NPR 4. And we get 5,040 different possible ways of arranging those 4 books taken out of a pool of 10 of them. How long would that take? If each are 5 minutes, that's 25,200 minutes. Divided by 60, that's 420 hours. Divided by 24 hours, that's 17 and a half days. That's a lot of time. Okay, but that's doable and quickly using your NPR button. All right, well, back to this example with the 85 recipients that caused trouble over here. What if we wanted to see, let's say instead of having all 85 recipients listed out at graduation, let's say that they just said, let's take a sample of 3 and let them speak. Well, who gets to go first? Who gets second, third? So if you wanted to know the number of permutations of 3 things out of 85, you could use 85 NPR 3. Yes, we could do the calculations, but you could just use that function and get 592,620 different ways of letting 3 out of the 85 recipients, arranging them as speakers. So permutations, the NPR button, you want to use that when you're talking about the number of arrangements of R things taken out of a larger set of N things. We didn't have to use it over here, right? It's just the number of different permutations of 9 things. You just use factorial. Combinations, what's the difference? Well, in combinations, you're simply taking you're asking how many subsets of that size do I have? So for example 5, here, and can you see it? Let's try that. Okay. Alrighty, so let's say that out of 17 representatives of the House Ways and Means Committee, we need to select 3 of them to be on the governing subcommittee. Now, it doesn't matter who was chosen, which one was chosen first, second, or third. All we need to do is just choose 3 people out of those 17. Why would anybody be concerned about this? Well, the House Ways and Means Committee is a very powerful committee, and the people on the governing subcommittee get to decide what bills are going to be voted on, what gets tabled. So these 3 people are going to be very influential. But let's say that there's 3 politicians who always seem to get to do everything. So somebody might say, well, actually, if you randomly choose 3 people out of 17, the probability that any one group of 3 would get selected to be on that committee should be a pretty low number, right? Well, how low? Let's see. So if the number of committees, subcommittees out of a committee of 17 that you could choose, this is read as 17 choose 3, that's 680. Why are these numbers so much smaller than the permutation numbers? Again, because order doesn't matter. If order mattered, then I could take these 3 people and say, oh, those 3 people could be ABC, or they could be ACB, or they could be BCA, or they could be BAC, or they could be CAB, or CBA. That's 6 different ways of arranging those 3 people. So the number of permutations of 17 things taken 3 at a time would be 6 times that amount, okay? But combinations, not quite such big numbers. So what's the probability that our local representatives, Honest Adele, Cheesy Major, and Loud Louie, all get to be picked to be on that committee? Well, if there's 680 such possible committees, then the probability that any one particular group of 3 people would be picked would be 1 out of 680. Okay. So, things to remember are that the number of permutations of n things taken r at a time is always going to be greater than, in fact, our factorial times greater than the number of combinations of n things taken r at a time. If order matters, as it does for permutation, when order matters, much bigger list, longer list. Another thing to remember is that even though you now know about permutations and combinations, not every problem you run into has to be done using those formulas or that function on the calculator. For example, how many 10-digit phone numbers are possible if the first 3 digits cannot be 000, 911, 311, 411, or 611? Typical type of question. Let me get over here. There, you can see it better. So notice, you don't need to use NPR or NChooseR to be able to do this. Just draw 10 blanks. If you draw 10 blanks for those phone numbers and ask yourself how many different digits could go in each spot, let's say if there were no restrictions at first. Well, then you could put in here any digit, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's 10 different digits if you include 0 as a digit. 10 can't be a digit because that's got 2 digits, right? So from 0 to 9, that's 10 digits. So 10 possibilities here. If no restrictions, 10 there, 10 there, 10 there, and so on and so forth. So if there were no restrictions, there would be 10. You multiply all these number of choices, 10 to the 10 number of phone numbers if no restrictions. Well, now they're telling us that we have to throw out the ones that look like, that would have the first 3 digits look like 000, 911, 311, 411, or 611. Well, each of those, for example, if you had 611 here, how many different numbers could start with 611 and have 10 to the 7 choices after that? And there's 1, 2, 3, 4, 5 of those. So let's exclude those 5 times 10 to the 70 numbers that are not allowed. Be all the ones that start with those forbidden first 3 digits. That means 10 to the 10 minus 5 times 10 to the 7. Your calculator can do subtraction arithmetic with scientific notation. So you get 9.95 times 10 to the 7 different phone numbers in this scenario. And notice, no NPR or CNR necessary.